switch mode power converters. So DC-DC converters are very important role is playing in like various applications like electric vehicles, renewable energy, and DC microgrid and all. So as the DC-DC converters are very important in various applications. So the inductors will play a key role in the DC-DC converters. So it is very important to know how to design these inductors. So in my today's lecture, so I'm not going to take any advanced converters. I'm just going to take one conventional converter and how to design that. For that converters, how to design these magnetic components, I'm going to present. So as we know, before going to start with the design of magnetic components, we need to know how to design a converter. So before that, so we have to see how the DC-DC converters are arrived, how this DC-DC converter concept is coming to picture. So we'll start from that, then we'll move on to the DC-DC converters. So for example, a DC source like a battery or a converter from a rectifier, so has the different voltage levels, and the load which is demanded by the various loads is a different level. So in order to match from the source to load, so we need to connect a DC-DC converter between a source and a load. So this can be achieved in different ways. So initially, so if I have a battery of 12 volts, so for my load which is demanding by 5 volts. So if I want to convert from 12 volts to 5 volts, so we can connect a resistor like this. We can connect a resistor in between the source and load. So by this resistor may be a variable resistor. By using this resistor, we can achieve the desired amount of voltage at the load side. So from the source side. But here, the moment when you connect a resistor between the source and load, the current will start flowing. So the current will start flowing from source to load. So let us assume the current I is flowing through this series resistor. So there is some loss will be appeared across this resistor, that is I square R loss. So the way of converting from DC to DC, this is the one way of converting from one level of DC voltage to another level of DC voltage. However, in this one, if you see, so it has some losses will be appeared. So this is, we can call it as the linear regulators. This is a lossy component. So most of the energy is wasting as a heat here in the resistor. So that's why switched mode power converters are becoming more popular. So how to avoid these losses? So we can able to avoid these losses. So we can achieve the efficient regulators. So here two ways we can achieve, we can make it this I square R loss will be equal to 0. So how to make it I square R loss will be equal to 0 in two ways. That is, one is by making resistance will be 0. By making resistance will be 0, that is the one way to make the I square R loss will be equal to 0. The another way is by making I will be equal to 0. So I will be, ideally speaking, I will be 0 at R will be infinity. So how can we achieve this that resistance is 0 and current is 0? So this can be achieved ideally by replacing this resistor with the any power semiconductor device, that may be a MOSFET or IGBT or GTO or SC or anything. So by replacing this resistor with the semiconductor devices like MOSFET, so ideally, so the on resistance, ideally speaking, the on resistance of a device will be 0. That means on resistance will be 0 means we can say that is R will be 0. And ideally, if when the switch is open, so when the switch is closed, ideally the resistance will be 0. When the switch is open, so the current will be 0 ideally. So but practically if you go, there is some RDS on will be there, and similarly there is a small leakage current will flow. So ideally speaking, so these are the conditions which we can obtain by replacing this resistor with the power semiconductor devices. So here by replacing a resistor with the a switch, that may be any power semiconductor device. So if you see here, when the moment when the switch is closed, so that means it is short circuited, the resistance will become 0, R will become 0. The moment when the switch is open, so there is no current flowing, so we can say that R is infinity. So the moment when the switch is open, R is infinity. The moment when the switch is closed, it is 0. So in this way, we can make it the I square R loss will be 0 ideally. So this is called the efficient way of convert DC-DC converters. We can also call as switched mode DC-DC converters, because here we are using the switching operation. So by replacing this single pole single throw switch with a double single pole double throw switch like this, if you see here, so the moment when the switch S is connected to T1, so that means, so if I am triggering the switch with the switching pulses like this, and the moment the switching pulse is given high, so the switch is going to turn on. When the switch pulse is removed, it is going to turn off like this. The moment when the switching pulse is given, so that means when this point P is connected at T1, so the whatever the input voltage which is there, it will be applied across the load. That means we can see the output voltage will be as the same as your input voltage at this instant of time. So that is, let us assume this is a dt time. So when the moment when the this point P is connected to this T2, so that means this is open. So that means it is shorted. That means the voltage across the load will be 0. So if you construct a DC-DC converters like this, so your output voltage will be not a constant DC. It is a variable DC. If you see here, it is a variable DC. How can we make this variable DC into a fixed DC, that is constant ripple free DC? So by using some LC filters, with this configuration, we can eliminate this ripples in the output voltage. We can achieve the constant DC voltage like this. So here the placement of this LC component, LC elements, so is depending on the converter. It is placed in various locations. So depending on the placement of this LC components, the conventional converters are 3 types. That is everyone knows, like a buck converter, that is also called as step down converter, and boost converter, step up converter, and buck boost converter, step down converters. There are many advanced converter topologies has developed based on this conventional converters. So for any advanced converters or this conventional converter, the design approach of the magnetic components will be same. So that's why in order to explain the magnetic components design, so in other way, the design of an inductor, so I'm going to discuss the working operation of the buck converter initially. From that working operation, we are going to get basic design parameters. If you want to design an inductor, so we need several parameters like inductance value, and also the maximum current which is flowing through the inductor, and the average current which is flowing through the load or inductor. These parameters which we need to obtain, so by designing any conventional converter or any advanced converter. So here first I will take up an example of a conventional buck converter. So I'll explain the design procedure of the buck converter. From that design, so we'll start understanding the how to design an inductor, how to find the number of turns, and how to find the what kind of cores we need to use, and how to find out so which type of gauge wire we need to use, we will see. So before going to understand the steady state analysis of any converter, first of all we have to know 2 important things. So let us consider an inductor. So the current flowing through the inductor is I. So the voltage across the inductor is VL. So under steady state operating condition, so the voltage across inductor, the average voltage across the inductor should be equal to 0. The average voltage across the inductor should be equal to 0. If the average voltage across the inductor is not equal to 0, so what will happen, we need to understand. Let us assume the current I is flowing through this inductor. So the voltage drop across this terminals is VL. So according to Faraday's law, we know VL will be L dIL by dt. So from this one, Li is nothing but N phi. So this is also nothing but N d phi by dt. This is a well-known formula. From this one, if we calculate flux pi, so the flux pi will be equal to 1 by N into integral VL dt. So let us assume the voltage across the inductor is not equal to 0. What will happen if it is not equal to 0? So it keep on integrating. So the voltage it is keep on integrating. Therefore, the flux also will increase. So as the flux is keep on increasing, at certain point the core will saturate. So the core will saturate. So if the core will saturate, so there is no role of inductor during that point. It will act as a resistor, right? So therefore, we need to take care of that the average voltage across the inductor should be equal to 0 under steady state operating condition. That is the one important parameter. The second one is let us take a capacitor. So the voltage across the capacitor is V. The current flowing through the capacitor is IC. So here the average current flowing through the capacitor should be equal to 0. The average current flowing through the capacitor should be equal to 0. So if average current flowing through the capacitor should not be equal to 0, what is going to happen? We need to understand here. So when the current IC is flowing through this capacitor, so the relation is the IC will be equal to C dV by dt here. So from this one, if you calculate the voltage will be V is equal to 1 by C integral IC dt. So now if you see the average current flowing through the capacitor will not equal to 0. If not equal to 0, so that means if it is not equal to 0, it keep on integrating. So therefore the voltage will build up, keep on increases. So at certain point of time, so every capacitor has some rating, that rated value. At certain point of time, so the voltage will reaches at a rated value and it will increase beyond the rated value. So therefore there is a failure of the capacitor. So therefore these two parameters we need to take care while analyzing any converter, that may be a conventional or high gain converters or advanced converters. So these are the two important parameters we need to take care. So here now we will try to see the working operation of this conventional converter so that we can able to find the maximum current and inductance value. So first we will see when the switch is closed how it is going to work. So the moment when the switch is closed, so here the switch will be closed, it will be short circuited. So when the switch is closed, the positive terminal of the source will be connected here, the negative will be connected here. Therefore here the diode will be reverse biased because the positive is connected to the cathode and negative is connected to the anode. So the diode will be reverse biased. So during this instant, the source will supply the energy to the load by charging the inductor. So here you can see, so this is the this is not the reference point. So this is the reference point. So this is the switching pulse. This is the switching pulse. So this is the on time. This is the off time. So I am turning on the switch for the DT time. So the moment when the switch is closed, so if you apply the KVL, so if you apply the KVL in this loop, in this particular loop, so if you apply the KVL, so this is VL will be equal to Vs minus V0. So this is VL, the voltage across the capacitor is nothing but the output voltage, this is Vn. So VL is nothing but the Vs minus V0. So here, so VL is nothing but L dIL by dt. So here if you calculate dIL by dt, this is Vs minus V0 by L. So as this is a buck converter, so in the buck converter, the output voltage is always less than the input voltage. The output voltage is always less than the input voltage. So therefore the slope will be positive. This is the slope. So the change in slope dIL by dt, this is the positive slope. So as this is the positive slope, you can see here our inductor current is increasing linearly. So it is increasing due to the positive slope. So this is dIL by dt, this positive slope. What is the voltage across the inductor? VL will be equal to Vs minus V0. So this is the higher value Vs, V0 is the lower value. So therefore the resultant value will be positive only again. So here this is the Vs minus V0 during the switch on time, So from this one delta IL, that is change in inductor current. So nothing but a delta IL, dIL is nothing but the delta IL, dt is nothing but delta t. So dIL by del IL by delta t. So del IL, that is a change in inductor current. So delta t is how much? So from 0 to dt, this is the delta t. This is the delta t during the switch on condition. So dt minus 0, that is dt. If we calculate delta IL during the switch closed condition, so delta IL during closed condition, it will be Vs minus V0 by L into, so the duration is on duration is dt. This is the change in inductor current, that is ripple current. This is the ripple current during the switch is closed from the instant when the switch is on to up to this time dt. So similarly, if you analyze, so when the switch is open, the moment when the switch is open, that means the moment when the switching pulse is removed, So that means there is no switching pulse. If you remove the switching pulse, that is gating pulse to the switch, it will be turn off. So the switch will be open circuited. So this will be open circuited. So and this is open circuited. So because due to the inductor principle, it will not allow the sudden changes in the currents, right? So in order to provide the path for the inductor current, the diode will be forward biased. The diode will be forward biased during this moment. So here, if you apply the KVL in this particular loop, so the voltage across the inductor, so this is the VL, this is the V0. The voltage across the inductor will be minus V0. VL will be equal to minus V0. You can see the voltage across the inductor. The moment when the switch is open, so the voltage across the inductor will become negative. This is a minus V0. It becomes negative. So the slope dIL by dt, the slope of the inductor current will be minus V0 by L. So this is also negative. This is also a negative slope. The meaning of negative slope means it is discharging. So it is discharging the moment when the switch is open. So during the time, so if you calculate the delta IL, that is ripple current, so delta IL during the switch is open condition, again this is del IL by del T will be equal to, so del IL is I want to calculate, so del T is nothing but, so this is the moment when the switch is open from this point to up to this point. The difference of this is T minus dt, it will be T into 1 minus D. So the delta T is nothing but 1 minus D into T. So this is slope is minus V0 by L. So the delta IL during the switch open condition will be minus V0 by L into 1 minus dt. So this is the when the switch is open. So once if we calculate the ripple currents during the switch on and switch off condition, so then we need to find the gain of the converter. Once if we calculate the gain, then we can calculate the maximum minimum currents. So you know the gain of the currents, how to calculate the gain or output voltage of the converter. So we can find in two different ways. One is the average voltage across the inductor should be equal to 0 under steady state condition. That is the one way to calculate the gain, and other way to calculate it is under steady state operation condition. The inductor current at the beginning of the cycle, and at the end of the cycle should be same. That means the change in magnitudes during this beginning and ending of the cycle will be equal to 0. That means del IL closed, that is during the turn on condition, del IL open, this is during turn off condition, should be the effective current should be equal to 0. So we have calculated del IL closed during the switch on condition, that is Vs minus V0 by L into dt, and del IL open, that is minus V0 by L into 1 minus dt. So this will be equal to 0. If we simplify this one, the gain will be, the output voltage will be V0 is equal to Vs by d. Here the gain is nothing but output voltage by input voltage, that is the d. The gain of the buck converter will be d here. So here another way to calculate the gain, that is under steady state operating condition, the average voltage across the inductor should be equal to 0, right? The average voltage, that is VL during switch on condition dt, VL during switch off condition 1 minus d into t will be equal to 0. So again VL will be Vs minus V0 into dt, VL will be minus V0 into 1 minus dt. So if we simplify this, so the output voltage will be V0 is equal to Vs into d. From this one again the gain, so this is the voltage gain, V0 by Vs will be equal to C. V0 by Vs will be equal to, so we can say this is like a nothing but a so DC equivalent of step down transformer. So if you see the turns ratio, it is like if you represent in DC, this is a DC transformer, step down DC transformer we can say. So here the maximum output voltage which we can obtain here is, so that the range of duty cycle is from, ideally it is from 0 to 100%. So ideally it is from 0 to 100%. When it is ideally it is 0 to 100%, but practically there are some constraints. So we can restrict some. So 0 it is not possible, and even 100% we cannot turn on the switch. So the maximum value ideally we can maximum output value we can ideally will get is, so that is less than or equal to Vs. The output voltage will be less than or equal to Vs we can achieve. So when D will be equal to 0, When D will be equal to 0, so it is V0 is 0. When D will be equal to 100%, we will get the V0 will be Vs. So now once if we calculate the gain, so we need to calculate the maximum and minimum inductor current. This is one of the important parameter, so to design an inductor. So from the conventional converter, if you clearly see the converter, so the average current, flowing through the inductor should be same as your load current. Whatever the ripple current will be there, let us assume, so this is your inductor current, this is the average current. This average current will flow through the load, and this ripple will be absorbed by the capacitor. The ripple current will be absorbed by the capacitor. So here, that means the average inductor current will be equal to the average load current. So the average value of inductor current, that is I am representing with IL, the average load current, that is IR, will be equal to V0 by R. So this is the average inductor or average load current. So now we need to find out the maximum and minimum currents, right? So if we go back to the circuit again, so here you can see this is the maximum current. So this is the maximum current. This one is the maximum current. This is the average value. So here maximum current will be equal to, so the average current, that is IR, plus, so the ripple will be from this to this point. So this is the del IL, but so this is only half. This is the del IL by 2. This is again del IL by 2. Del IL by 2, del IL by 2, it will become del IL. So maximum will be IR plus del IL by 2. Similarly, I minimum will be equal to, I minimum means, so this is the I minimum. This is the I minimum. So I minimum will be equal to IR minus del IL by 2. IR minus del IL by 2. This is the maximum and minimum currents. So now if we calculate the maximum and minimum currents, so from here del I max will be equal to IL plus del IL by 2. So already we know IL is nothing but average inductor current V0 by R. Del IL we know. So 1 by 2 I am taking common. Del IL we have obtained. So during the switch off condition, that is V0 by L into 1 minus dt. So if you simplify this, this is the maximum current. So this is the one of the important parameter which is required to design an inductor. Similarly, so the minimum current. So this is the one more important parameters to find out the critical value of inductance. So this is the minimum current, right? This is the minimum current, that is IL minus del IL by 2. IL minus del IL by 2. Simply it will be, we are getting negative V0 into 1 by R minus 1 minus D by 2 LF. So here this is the minimum current. So in order to operate your converter in continuous conduction mode, so first of all we need to find out the critical value of inductor. The meaning of the critical value means, so during this critical value of inductance, the converter will operate under boundary conduction. That means, so it will the current flowing through the inductor will reach the zero. It will reach the zero immediately. It will rise. This is the boundary conduction mode. So continuous means the inductor current will never comes to zero. It will never comes to zero. This is the continuous conduction mode. So discontinuous means that
next week కాదు మేము ఏదో పెట్టాంలే ప్రోగ్రామర్ అంటున్నారా.
So the moment so here during the boundary discontinuous conduction mode, the inductor current will come to zero and it will stay at zero sometime. So this is called the discontinuous conduction mode. So here, so I'm now the critical value, we are in order to operate the converter in boundary conduction mode. So the minimum inductor current should be equal to 0. I minimum should be equal to 0. So if you make I minimum is 0, so if you make I minimum is 0 and if you calculate the value which is coming, this is the L minimum. This is also called as critical value. So from this one we can find the critical value of inductance. Once if you know the critical value of inductance, if you want to operate your converter in continuous conduction mode, so LCCM should be greater than or equal to L critical. So that is usually we will take 1.25 times of critical value, so such that the converter will operate in continuous conduction mode. Again, so there is one more parameter will be decided the L value in continuous conduction mode depending on your application. If you want to allow more ripple current in the inductor, you can take little lesser value. If you want to allow less ripple, you want to increase the L value. Similarly, if you want to operate in discontinuous conduction mode, so your critical this L value in discontinuous conduction mode should be less than or equal to L critical. So like this, you need to design your critical value. From that, you need to find out the L value for the different operating modes. Once if you calculate the L value, so that is L value already you can design by substituting the various parameters, and I max also we have obtained, and also the average value of inductor or load current. So as I mentioned, so L value can be designed in another way also, like L will be equal to V0 into 1 minus d by del ILF, where del IL is the ripple current of the inductor. So how much ripple current you want to allow? So based on that, your L value will be decided. Usually 10% of your load current will be 10% of your load current will be will consider while designing an inductor in order to reduce the inductor ripple. So again, it is depending on your application. If your application you don't have any issues with more ripple, then you can increase your ripple, so that if you increase your ripple, your L value will reduce. So if L value will reduce, again the size of the inductor will reduce, the overall converter size also will reduce. So in this way, you need to design your inductor. So this is the way to design the capacitor. So here, this is the ripple current which is flowing through the capacitor. So if you see, let us assume this is the average value. Let us assume this is the average value. If it is an average value, it is looking like a inductor current. So what is happening? The average value is flowing through the load, and the ripple current is flowing through the capacitor. So if you find, from the familiar equation that the charge Q will be equal to C into V0. So from this one, if you find out the change in charge delta Q, so that is half into width into this height delta L by 2. So if you calculate the charge, then if you substitute here your ripple voltage, that means how much ripple you want to allow for the load voltage is decided by this value. From this one, you can calculate the C also. C will be T into del IL by 8 into del V0. Where, so if you want to get the only 1% of your output voltage, so in such a way that your capacitor will be decided. So this is the way to design a converter. Once if you design the converter, so we got the parameters which is required to design inductor, that is L value and IM value we have already obtained. So now we'll see how to design an inductor. So that is the one part. Designing a converter is one part. Designing an inductor is another part. So there are several approaches to design an inductor. So in that first one is trial and error approach. In this trial and error approach, usually the people will twist some random number of turns on the bobbin. So by adjusting the number of turns, they will come up with their designed value. But that is not the proper way to design an inductor. So this will lead into many problems. It may sometimes it may goes to saturation level, so that the role of inductor will not be proper. So this is not the recommended practice to design proper inductor for the DC-DC converters. So there is a area product approach is there. This is the best practice to design an inductor for any converter topologies. So now we'll try to understand how to design an inductor by using area product approach. So there are several steps which is involved in this area product approach. So first we need to calculate so here you can see the one kind of core. This is the ferrite cores. This is the simple example. I will show you later. So this is the PQ core. So this is called the PQ core. So there are different cores are there, like a EE cores, EI cores, right? Part cores, UU cores, and toroidal cores. Many types of cores are there, and also PQ cores. This is the PQ core, one of the very effectively used for the switching mode power converters. So in this, first we need to calculate the area product. So how to calculate the area product? So first of all, if you want to calculate the area product, we need to know how much energy the inductor has to be handled. So how much energy the inductor has to be handled, we need to find. How to calculate this one? The energy will be the well-known expression, that is E will be equal to half into LIM square. So these are the two parameters which we have obtained from the design of the converter, right? This is the way to calculate the energy. Once if we calculate the energy, right? So now the window area of the core should accommodate, that is this is the window area. This is the window area. The window area of the core should accommodate n number of turns with cross sectional area A. So for that, so here this is kW AW will be equal to NA. So here this is the window utilization factor. kW is the window utilization factor. AW is the window area. AW is the window area. N is the number of turns. So n number of turns we need to accommodate in this particular window area, and number of turns we need to accommodate in the window area with a cross sectional area of A. So that's why kW AW will be N into A. So from this one, so we know area A will be equal to I by J. So where I is the average current which is flowing through the load or inductor, where J is the current density. So I is the average current, and J is the current density in ampere per mm square. So from equation number 2, so if I replace the area with this term, that is I by J, so kW AW will be equal to N into I by J. Once if you substitute this one, so we need to define what is crest factor or core utilization factor. This is the window utilization factor. This is the core utilization factor or crest factor. So crest factor will be maximum value by RMS value. That is the maximum value, that is nothing but the peak value by RMS value. So I is the RMS. So usually this crest factor, so we need to calculate depending on our nature of the inductor curve. So Kc will be Im by I, that is peak current by RMS current. So from this one, if you substitute here, so this RMS value if you substitute, so we will get this expression. So Kc Kw AW into J, that will be equal to N into Im. I am substituting from this one RMS value. RMS value will be I will be equal to Im by Kc. Im by Kc. So Im by Kc, if I substitute, Im will be here, Kc is coming this side. This is the crest factor, this is the window utilization factor, this is the window area, this is the current density. So from Faraday's law, Faraday's equation, so E will be equal to L di by dt. So that is also called as N d phi by dt. So here flux will be equal to, so area into magnetic flux density. If you substitute here, so this will be N into AC into dB by dt. So from Faraday's law. So and LIM, so LIM will be equal to N into AC into Bm, which we have calculated. So now if you simplify equation number 6 in by substituting equation number 6 in equation 1, we are going to get the energy will be equal to half into N into Im AC Bm. So this is the equation. So again from this one, so if you calculate Im, so from previous equation if you calculate Im, so from equation number 6 Im, and if you substitute here, we are going to get the area product. So the area product AP will be equal to the core area into window area. So if you simplify this is the 2E by KW KC J Bm. This is the very important equation, the area product. So once if we calculate the area product by substituting the energy, window utilization factor, core utilization factor, current density, magnetic flux density. So once if you calculate the area product, so you need to select a core from the data sheet. So for that particular core, the area product should be more than what we are getting. So that means, so here usually for ferrite cores, the window utilization factor will be 0.7, it is constant. Similarly, the core utilization factor will be 1. So the Kc will be 1. So if you substitute all these parameters, you know Kw, Kc, J is the current density, that is already I have given the value 3 ampere per mm square. So Bm is the magnetic flux density. This will be 0.2 Tesla for the ferrite cores. So once if you substitute all this data, we will get the area product. From now onwards, we need to select the core which is having the area product of more than what we have obtained. So from now onwards, we need to use that particular data. So then how to calculate the number of turns? So from previous expression, that is LIM will be equal to LILM will equal to N into AC into BM. From this one, number of turns N will be equal to L into IM by AC into BM. So N into L into IM by the core area into magnetic flux density. In this way, we can calculate the number of turns. This is the calculation of number of turns. Now, once if we calculate the number of turns, so there are different types of gauge wires are there depending on the cross-sectional area. So which gauge wire you need to select, again we need to calculate. So here the cross-sectional area of the wire can be calculated from this expression, that is A will be equal to I by J. I is the average current. We need to consider the RMS current. We need to consider the RMS current for the calculation of cross-sectional area. This is the current density. Once if we calculate this cross-sectional area, again there are different data sheet will be there for different gauge wires, standard gauge wires. So different gauge wires, different cross-sectional areas will be there. Whatever the cross-sectional area which we are getting here, so we need to select a gauge wire which is having the cross-sectional area of more than the value what we are calculating. So next, so whatever the design we have done, so the design is correct or not, we need to cross check. So by using the following condition, that is AW KW will be greater than A into N. So we need to cross check this one, because this is the AW is the window utilization window area, KW is the window utilization factor, A is the cross sectional area, N is the number of turns. All these things we have calculated. Once if you substitute all these values, if this condition is satisfying, so then our design is correct. If the condition is not satisfying, again we need to go back to the area product. So whatever the core which we have selected, so we need to go with a somewhat higher value than what we have selected in the previous case, because with that particular core our design is not satisfying this condition. So in that condition we need to go with the higher value of a core. Then again we need to repeat the same procedure. So this is the way to design an inductor. But here again we need to fix the air gap length. How to fix the air gap length? So to calculate the air gap length, so this is the LG will be equal to mu naught N square AC by L. If we calculate, we will get some value here. So that much thickness of air gap you need to use while winding in a practical inductor. We will see with one example. So this is the appendix data, so which it is required while designing an inductor. So these are the different cores. These are the part cores. This is the double E cores. This is the double U cores. This is the toroidal cores. Other than this, there is a PQ, ETD, EI. Different cores are also available. The data, the data will be available in the internet. You can find. So this is the appendix for the cross-sectional area A. So here the cross-sectional area A. This is the data which we need appendix which we need to use. So let us assume. So from the design of a converter. So these are the required parameters for my converter to operate. That is. So from the design of a buck converter, I am assuming these things. That is, L will be equal to 100 microhenry. So maximum inductor current will be 3.24. That is the maximum current which is flowing through the inductor will be 3.24 amperes. The average current will be 1.8 amperes. So these are the parameters. For these parameters, I need to design an inductor. That is, the inductor should give the value of 100 microhenry. Right, so and it has to it can able to capable of allowing the 3.24 amperes of maximum current. So for that we need the data for ferrite cores. This is the fixed data for ferrite cores. The current density will be 3 ampere per mm square. It is in meter square. It is 3 into 10 power 6 ampere per meter square. It is in meter square. So this is window utilization factor. It is fixed. The core utilization factor 1 for the square wave. For other kind of waveforms, you need to calculate, that is IC will be equal to maximum current by RMS current. Maximum current by RMS current. If you find the maximum current and RMS current of that particular waveform, so if you divide a maximum current by RMS current, you will find the core utilization area. So approximately you can consider 1 for respective of the nature. So more or less it will be around 1 only. So the magnetic flux density will be 0.2 Tesla. So here our first step is to calculate the energy, right? So if we calculate the energy by substituting L will be equal to 100 microhenry. So the maximum current will be 3.24. So if we calculate the energy, so here it is 524.88 microjoules I am getting. So this is that means, so the inductor should able to capable of so this much energy it has to accept, right? 524.88 microjoules. So once if we calculate the energy, the area product, that is area product will be, so window area into core area, that will be equal to 2 times of energy by window utilization factor, core utilization factor, current density and magnetic flux density. So by substituting all these values in this expression, so here I am getting the area product will be 2.916 into 10 power minus 9 meter power 4. So this I am converting into millimeters. So if I convert into millimeter power 4, so it is 2916 mm power 4. So here area product I am getting is 2916 mm power 4. Now I need to select a core, so that particular core is having the area product more than this value from the appendix 1. If I go back to the appendix, here, you can see, so here this is the area product. This is the area product. So here area product they mentioned AP into 10 power 4 mm power 4. AP into. So here we are getting it is mm power 4, right? So here they have mentioned area product AP into 10 power 4. AP into 10 power 4 mm power 4. That is units is same, but whatever the value is here, so you need to multiply with 10 power 4. So what is our area product we got? That is 2916. If you see that P18 by 11, so here the area product will be, if we multiply with this is 1140. The area product of P18 by 11 is not sufficient as for our design. If you go with P26 by 16, how much is the area product here? It is 0.498 into 10 power 4. That is 4980. How much we got? We got 2916. That means the area product of this particular core is more than what we have calculated. Therefore, so we can go with this core. This is the one core which we can design. This is one way. So for example, if you don't have a part course, so then you need to go with the EE course. So here if you see the EE course, so if you see the first one, E20 by 10 by 5. So here it is 0.149. If you multiply with 10 power 4, it is 1490. 1490 is lesser than the what we have calculated. Again, if you check with E25 by 9 by 6, so it is having 0.312 into 10 power 4, that is 3120. This is also best suitable for our design. This core is also best suitable for our design. So now instead of this, I am going with this one, because if you go with this, again it is P26 by 16 is the higher size than this one, because anyhow it is suitable for my design. I am going with E25 by 9 by 6. So the core will be for this particular value, the core will be E25 by 9 by 6. So for this particular core, we need to know how much is the core area and how much is the window area. This is the core cross-sectional area. So this is the core cross-sectional area AC into 100 mm square. This is the window area. That is AW into 10 power 4. We need to consider these two values. This is 40 into 100. It is 40 mm square. So 78 into 100, it is 78 mm square. So here you can see, so the core area will be 40 into 10 power minus 6 m square. That is nothing but the 40. That is nothing but the 40 into 40 mm square. If it is converted into mm square, your core area will be 40 mm square. So here it is in meter square. We are always using mm square, that is 40 mm square. Similarly, your window area will be 78 mm square. From now onwards, we need to use this data. We need to use this AC, this AW, and the area product will be 3120 mm square. From now onwards, we need to use this data, not this one, right? So here, if you multiply this area product and the window area, it should be approximately equal to this value. So because area product will be equal to core area into window area. If you multiply your core area and window area, it should be approximately equal to your area product. So once if you know these values, now we need to calculate the number of turns. So number of turns, so we know the expression from the inductor design. So LIM by core area into magnetic flux density. So L is 100 microhenry, IM is the maximum current. So core area is how much? Core area we have obtained, that is 40 mm square. So that is 40 mm square. If you substitute here, the magnetic flux density is 0.2 Tesla. So it is coming approximately 40.5 tons. So if you round up to nearby value, it is 41 tons. The number of tons will be 41. So similarly, if you calculate the gauge wire, so how to calculate the gauge wire? So the area of cross section will be equal to I by J. So this is the average current. So current density. If you substitute the average current and current density, so here we are getting 0.6 into 10 power minus 6 meter square, right? So it will be around 0.6 mm square in terms of mm square. So now we need to select a gauge wire which is having the cross sectional area more than the 0.6 mm square or approximately 0.6 mm square. Now go back to the appendix 2. You can see here. So from this appendix, they have mentioned the area of cross section for the different gauge wires. This is SWG, gauge number SWG, that is standard gauge wire. That is standard gauge wire. The standard gauge wire will be, so from 50 to 8 they have mentioned. So here you can see area of bare conductors in mm square. Area of bare conductors in mm square. This is the area of the conductor in mm square. How much we got? We got 0.6 mm square. So where it is there? If you see here, SW21 it is having 0.5189. This is not suitable for our application. So if you see SW20, that is standard gauge wire, so the area of conductor will be 0.6567, right? So this is approximately it is near to more than the 0.6. So that means, so we need to use the gauge wire of 20. So the standard gauge wire will be 20. We need to use, that is SW20 is the proper choice. That is 0.6567 into 10 power minus 6 m square or 0.6567 mm square. We need to use from now onwards. That is area will be equal to 0.6567 mm square. Now we need to cross check. So how to cross check? So this is the AW KW, that is the window area, 78 into 10 power minus 6 in meter square. So window utilization factor is 0.7. So if you multiply these two, this is the product of AW KW. Similarly, the product of AN will be this one. So if you see AW KW is greater than the AN. AW KW is greater than the AN. That means whatever the design we have done, so that is the proper design. So therefore, so whatever the design number of turns gauge wire which we have obtained from the inductor design, that will be fit into the design code. So again, if you want to calculate the air gap length, LG will be mu0 n square AC by L. So if you substitute all the data, So you will get the air gap length of 0.84 mm. So that means the meaning of this one is you need to select the air gap of 0.84 millimeters. So then only it will give the accurate value. Otherwise, you need to again adjust number of terms, because if it is not exact value. So here I'll show you the one inductor which we have designed for our application. So yeah, so is the cursor visible?
Sure.
You can see these are the cores. You can see these are the cores. These are the one type of PQ core, PQ 26 by 25. So as for our design, we are getting WE 25 by 16 by 9, but unfortunately we don't have that particular core. So in order to show the how the inductors are designing, so I have made one inductor with this particular core. This is the PQ core. So this PQ core, so we need to twist the windings. This is the bobbin. This is called the bobbin. So here, if you see the number of turns, so the turns which I have wounded here, this is not for the our design. So this I made for the 40 microhenry. For 40 microhenry inductor, so I am getting approximately around 9 turns. So this is the bobbin. On the particular bobbin, we need to twist the windings by using the gauge wire. So you can see this is the gauge wire, copper wire. So like this, there are different types of copper wires will be available. This is the SWG21. Like that, from SWG1 to 50, depending on the current rating, there are different types of copper windings will be available. So this by using SWG21, I have designed a inductor that is for 40 microhenry. So once if you wound the windings on this bobbin, so this is the core. So this is the core. So on this core, so you need to place this bobbin in between these windings like this. So in between whatever the air gap you are calculating, you need to place. Then you need to use some tape or some araldite in order to fix this one. If we have calculated for 40 microhenry, so we are exactly getting at 40 microhenry with a resistance of 90 milliohms. So this is the way to design the inductor. So if you have any questions on this design, so you can ask me. Let me see. So these are the references which I have used to make the presentation, that is design of magnetic components for switch mode power converters. This is one of the standard book, especially for this inductor design and also transformer design, and also Daniel W. Hart, that is power electronics textbook. Any questions? I'm ready to take.
This participant, if you have any questions, you can ask now. The forum is open now. Hopes no questions from participant.
Okay, thank you. First of all, I'd like to thank the management and the principal, Dr. JVR sir, and HOD Professor Asif sir, and also organizers for giving this opportunity to share my knowledge with the participants. Thank you.
Yeah, thank you, sir. And good morning to one and all present here. I am Dr. K. Murugaperumal. and I'm here to present the vote of thanks for this today's IEEE PES workshop on the advanced power converters first day session. I would like to thank our keynote speaker, Dr. Ramanjanaya Reddy, School of Engineering and Science, SRM University, Andhra Pradesh campus, for accepting our invitation and enlightening us with his valuable knowledge. His presentation was very informative and knowledgeful sessions. He, apart from the normal presentations, SAR went to the deep insight to the topics and revealed many interesting facts. The point where Dr. Reddy Garu shared with us about the design of magnetic components and for the switched mode power converters is really informative session. I'm pretty sure that knowledge is really helpful for our future knowledge enrichment activity. Once again, I would like to thank our Ramanjanaya Reddy sir for taking out the time from his busy schedules and spend the knowledge with us. Thank you, sir. And my sincere thanks to Dr. Muhammad Asif sir, head of the department, Vardhaman Engineering College, for his moral support to conducting this type of technical events. And my heartfelt thanks to IEEE PES student chapter coordinators, Dr. Karpaya sir and Dr. Praveen Kumar sir, for organizing this type of continuous and motivated session for the students community and the faculty community. Last but not least, my grateful thanks to all the participant faculty members of the VCE and research scholars and the students members for your eagerness to learn the new things. Once again, thank you all. Again, we'll meet on the next tomorrow sessions on the 10 o'clock for the second session of this workshop. Thank you all. Thank you, sir.
Thank you. Can I leave?
Yes, sir. Yes, sir. Sure, sir. Thank you very much, sir.